So hello everyone, myself Sumit Kumar with my friend Vivek Ranjan took participation in the Altair flux motor design contest under the supervision of Dr. Ankit Rao sir. Uh, we are currently pursuing electrical engineering in second year, IIT Bhubaneswar. So the motivation of this project was to build a high RPM BLDC motor for learning and demonstration purpose. So our main focus was to the main focus of this application was for drones, which carries a high payload. So the key objective was to make a motor with optimum high speed and optimum torque. So the main design consideration we included was KV rating. The motor should have a high KV rating, while stator and rotor configurations were made for to make it highly efficient. Topology of motor. We choose 6 slot 8 pole inner rotor BLDC motor for high torque and high RPM. Stator inner diameter was 38 mm and outer diameter was 85. Uh, while the rotor outer diameter was 34 and inner diameter was 6. These parameters were set as per to get the air gap length uh, less than 2 mm. This would increase the efficiency of the motor. Status slot. The status slot. We first thought to have a air gap of less than air gap of 1.7 mm, and the number of coils in each slot would be 70 coils. So there would be 140 coil sites in each slot. So uh, so to achieve this, the parameters we set was height of the slot and width of the teeth to be uh, this, and the outputs were this. Stator winding enameled copper wire of diameter 0.8 mm were used, uh, while these these coils were shot in Y fashion. The number of coils was set to be 70 coils in each slot, 140 turns of each coil side in each slot. The winding factor was coming out to be 0.866, while the resistance per phase was coming out to be as follows and inductance was as follows. The windings were done in Y connection, and we can see the connections over here. The simulation back EMF test was done in the simulation. Test speed was 1000 rpm. So this is the uh, voltage generated in the stator coil, and as you can see, the sinus. This is a sinusoidal wave with harmonics attached to it. Uh, the reason of the harmonics can be explained by a spatial distribution of permanent magnet, and also by coil pitch. As the coil pitch is not exactly 180 degree, it will have harmonics attached to it. Uh, Flux linkage versus rotor angular position. So flux linkage is the first fundamental harmonic. So it would be purely sinusoidal, and this is the main cause, uh, main magnetic field, which is going to induce EMF in stator coil. So because this is a sinusoidal wave, the EMF induced in the stator coil is a sinusoidal, and this is the first harmonic, which is flux linkage. This is the first fundamental harmonic. So this would uh, this would define the waveform of EMF, and the flux density in the air gap versus rotor angular position. So we can see this is a lot distant magnetic field. The reason of this can also be explained by the same reasons, uh, because the angular distance between rotor poles, and also because of coil pitch and winding factors. Uh, as you can see, the back EMF measurement confines this. The induced voltage is about 0.08 volt on 1000 RPM. So we can see that the EMF induced is quite low, which means the magnetic field is quite weak, and the vector potential defines it as the magnetic field lines in the machines are quite low. We can see it in the picture. So uh, when the motor is going to work, it will have a high speed with a bit of torque in it, because the material we are using is a plastic. So this is the working demonstration of our BLDC motor. This is the whole setup. This is the computer we are going to send the signals to Arduino, through which it will pass the PWM signal to ESC, which will drive the motor, BLDC motor. We are using this as a voltage supply, and we are going to check the speed of this BLDC motor through this oscilloscope by getting the current waveform from current probe. So this is the working demonstration of our motor. We will start the motor at 20% throttle. At 20% throttle, the voltage set at 10 volts, while the current carried by motor is 0.18 volt ampere. As there is no load on the motor, the current is quite low. So as we know, this ESC works on a feedback loop, so we cannot directly determine the speed of the motor. So we will use the current flow. Using the oscilloscope, we will get the current in the one phase of the motor, so that we can calculate the frequency, and then we will calculate the speed of the motor. So the waveform coming over here is as you can see, this is a trapezoidal waveform in the one phase of the motor. We can check over here the frequency is coming out to be 480 Hz, which corresponds to 7200 RPM of the motor. So this is this motor has a high kV, which means it will have a high RPM motor. So on 30% of full throttle, the voltage around the motor is 9.9 volts, while the current carried by the motor is 0.24 ampere in per phase of the motor. The waveform is red trapezoidal, and the frequency coming over here is 700 Hz, which corresponds to 10,500 RPM.